back there. I think there is some rules about coffee in the room, but I forgot it. Maybe Yeka remember it properly. Are we allowed or
The
not?
coffee room, I don't remember anything.
You don't remember, okay. That's it. That's the rule. This is the way. So the presentation. So I want you to introduce our well, twin sister. We can say now. It's more than sister. We're twins now. Twin conference, which is what's the name actually? Is it okay? You tell it. And which happens to be in Brittany. No, in an island somewhere in the UK. Yes, exactly. So please.
Right. So only Mum can tell us apart these days because we're twins. We are the older. No, we're not. Actually, we're the prettier twin. See. Anyway, this year it's all about XMLPrague. Next year, about the same time, so the first half of June, in the UK, in London, there will be a new edition of Markup UK and not XMLPrague. So this is obviously quite confusing. And so we are here to answer any questions you might have about this later on. Now, tonight, there will be a demo jam, and one of the prizes, by far the best prize in my esteemed view, is a full pass to next year's Markup UK. So, and for anyone attending tonight's social dinner, there might even be some other surprises. So, attend. Make sure you're there. All right, anything I missed? Okay, so thanks, and see you next year.
Thank you. Yeka, you wanted to...
Yeah, we have one more thing which we would like to share with you. I will do a few clicks here to show you image of this gentleman. Probably many of you know the Liam Quinn. He had spoken here several times and it's well known in XML world. Unfortunately, he got cancer recently and he's running campaign to cover some expenses. So we decided to help him a little bit. So if you will send some money to this campaign during the conference time, you can obtain some vintage XMLPrague t-shirts like this. So just send some money to Liam using this campaign and then just visit the registration desk, and there is limited number of those t-shirts, and we also have few t-shirts from 2018. So thank you very much. And if Liam is watching us, hi Liam. And just to make it easier for you, if you will just go to the XMLPrague homepage, there is a link to the recent post, and in this post there is a link to this campaign, so you can easily find a link to support Liam. Thank you very much.
Thank you. So now let's move to the first presentation of the second part of the morning about expression elaboration by Michael Kay.
Thank you. Is this working? Good. I'm Michael Kay. I'm the founder of Saxonica and developer of the Saxon product, which I hope you are all using, and if you're not, we'll have to change that. I'm talking today, and I apologize for being the fourth old man in a row to be speaking to. But the term elaboration here is a bit of homage, as they say these days, to Algol 68, which was the sexy new technology when I started in the business, and is the way they described expression evaluation in effect. The talk is about trying to find a new and better way of evaluating expressions that brings together the benefits of code generation with interpretation, which are the two ways we do it currently. And I'm going to start by talking about interpretation and code generation and the advantages and disadvantages of both. So let's start with a warning that this project hasn't so far been 100% success. We've learned a great deal from it, and we've got benefits from it, and some of them weren't the benefits that we were expecting. And I think it's useful at a conference to share what we've learned and share what works and what didn't work, and to also share some of the things that we still don't understand about the results that we're getting. So the warning symbol says that there's roadworks ahead. It's not a clear route to the end of the tunnel. So expression trees. We've had introduction from Stephen this morning about how you can parse things into trees, and I'm sure the concept of parsing into expression trees is fairly familiar. Here's an example of a simple XPath expression, a comparison expression involving comparing the variable $x with the result of an arithmetic expression, and you build that into a tree of constructs. And it's the job of the parser, the compiler, to create an expression tree like that. And we're now concerned with what happens to that expression tree from then on. Yeah, I won't say any more about that at the moment. So if you're interpreting an expression tree, then in pseudocode, what you have is a class. And in an object-oriented language, you have a class for each kind of node in that expression tree. And each of those classes has an evaluate method. And the evaluate method, in this example, it takes some context object, which is what you get as a handle for all the variables and the context item and things like that. And the implementation of that evaluate method embodies the semantics of what that expression actually does. And if it's a comparison expression, that it evaluates the operands and then it compares them. If it's a variable reference, then it looks up the value of the variable and returns that. If it's arithmetic. So I've simplified it obviously by delegating most of the work in this example to a comparator object or a calculator object. Yes, Stephen?
Is the comma in the third line a mistake?
Yeah. Oh. Thank you. Yeah, that's a dot. But it's only pseudocode anyway. It's only pseudocode. This isn't the real code. The real code is obviously far too long to put on a screen. But a couple of things to draw out there. Firstly, the first thing that each expression has to do is to find its operands. And actually finding the operands on the tree is a lot more work than we would like. And the reason for that is that the tree that we use at runtime is the same as the tree that we build at compile time. And the tree we build at compile time has an awful lot of information about types and inferences and options that aren't actually used at runtime. And the tree is designed so that we can do manipulations on it, and that involves a data structure that's actually more complex than we would like to have at runtime. The second thing to draw out is that this is very highly polymorphic. So we've probably got, a couple of hundred different expression types. It's something between 100 and 200, I think. And they all have an evaluate method. And so you need to, the performance of this, and I should stress we're talking about percentage points in performance here. Someone told me once that the world economy, the world GDP can be boosted immensely by finding a 1% improvement in the process for producing sulfuric acid. And we're a little bit at the stage now with XSLT where it's a bit like producing sulfuric acid. It's something that everyone's doing, and a 1% improvement actually is something worth fighting for because of its multiplier effect. So we are looking for small improvements now in a mature technology. That's one reason why we're now looking quite closely at the way Java actually executes our code. And the way that Java handles polymorphism is part of that. We've been doing a lot of detailed looking at exactly what the just-in-time compiler in Java does with our code and how it handles the polymorphism and whether there are ways that we can improve that. This is what they call megamorphic. Megamorphic means you haven't just got 3 different implementations of a method, you've got hundreds. And the way JIT handles that it does impose a significant overhead. I'll go through this slide very quickly. I've taken this isn't the full expression tree that I showed earlier. This is a very simple expression minus $x. So you've got one operator and you've got a variable reference. So there's 2 nodes on this expression tree, and the bytecode for the first part is evaluating $x, and the bytecode for the second part is evaluating the unary minus operator. And that's actually real bytecode. That's what we generate, except I've added the comments, and I've abbreviated it to fit on the line length. But what we do is we load the context onto the stack. We invoke a method to get the stack frame. We then get the 0th element of the stack frame. We've calculated in advance that this particular variable $x is going to be at position 0 in the stack frame. And that's getting the variable, so sort of 5 instructions in bytecode, and then another 5 instructions to do the unary negation. But most of the work here is actually calling a method in the runtime library called the negate method. Actually, that negate method is 1 line of code. And what becomes significant in Java execution is that line of code can be inlined, because it's a very simple method, the negate method, and inlining it actually reduces the overhead, because it means that instead of 1 instruction to do the negation, you've got about 6 instructions to do the function call before you can do the negation. So the overhead of finding the code you want to execute is what ends up dominating both the bytecode case and the interpreted case. And it turns out that actually we've already, one of the spin-offs we got from this exercise was discovering that code can be improved. And the way it can be improved is by, instead of casting to a numeric value, we actually know from our own type analysis that $x is going to be a double value. And so we can actually cast to a more specific type. And if we cast to a more specific type, then the JIT compiler isn't polymorphic anymore. It knows that there's only 1 relevant implementation of the negate method, and it can inline that and avoid the polymorphic method call. So you really have to do some very, very precise analysis as to what's going on in order to find those micro-optimizations. So what's the problem with interpretation? Well, half the time you're spending deciding what to do rather than doing it. You are walking around the tree, you're examining conditions at runtime that you could have known at compile time were never going to be satisfied. We do as much as possible of doing that work early if we can, but there's still a certain number of things that you do at runtime that are unnecessary because you could have done them early. Navigating the expression trees are cost. The code is very highly polymorphic, as I've mentioned. And the other thing is that you get poor locality of reference. So the performance of modern hardware doesn't depend on how many instructions you execute. It depends on how much data you transfer between the main memory of your computer and the CPU. So it's the memory bandwidth between it's the bandwidth between the memory and the CPU that really determines performance, not the number of instructions you execute. And for that, getting locality of reference with your data, so that if you pull in 1 bit of data, then the next bit of data is likely to be in your cache already, is important. And the other thing that's important is the pipelining of instructions. So the processor can predict what the next instruction is going to be. And it turns out that both of those things are actually quite poor with an interpretive structure like this. On the other hand, what's the disadvantage of bytecode generation? Bytecode generation has the advantage that we bring together the code for a whole expression. So as we saw with the -$x example, It was bringing together the code for evaluating $X and the code for evaluating minus into a single lot of Java code with no overhead calling one from the other. So we were doing our own inlining of the code to create a single method for the expression. What's the disadvantage? Well, actually generating the code is expensive. So we end up doing it very selectively. We identify the hotspots. We only generate byte code for the hotspots. That involves its own overheads as to monitoring what code is being executed most frequently. There are a lot of sort of operational issues with the fact that if we do too much bytecode generation, we run out of memory, we hit limits on the size of methods or classes. So we have to do a lot of sort of failure management to make sure that we don't fail because of those limits. Debugging the stuff is an absolute nightmare. I mean, I do not like it when people find bugs in the bytecode. I don't like it when I make a change to the bytecode and it doesn't work. Because it means you've got 3 hours work working out what on earth is going on. That means maintainability is difficult. As the product develops, keeping the bytecode up to date and working functionally is hard work. And then the focus of this project is the problem is that bytecode only works on the Java platform, so it's very Java specific. And finally, the bottom line is that the performance benefits of it are actually quite modest. If we'd known what the performance benefits of doing bytecode generation were before we started, then we'd have never done it. Because it's only giving about 30% in the best case, 5% in a lot of cases, and 5% is certainly not worth the investment we've put into achieving it. On the other hand, having done the work, you don't want to throw away that 5% and throw away your work. So we were looking at alternatives. Now the background for this project, why did we want to re-examine this? Why did we want to rethink what we were doing? Was Saxon on the .NET platform. So until Saxon 10, we built a product on .NET by converting the Java product using technology called IKVM, which translates Java bytecode to .NET bytecode, in effect, at that level. And because that technology worked by translating at the bytecode level, it actually magically converted the bytecode we generated as well, which was astounding to see that working, because we didn't have to do anything to make that happen. But we could actually generate bytecode for bits of the expression tree, and IKVM would, on the fly, translate them into .NET code and execute that. So we got bytecode generation for free on .NET. The problem was Microsoft pulled the plug on .NET Framework and announced that the future was .NET Core, which is all the same APIs and architecture, but it's a completely different implementation underneath. And it meant that IKVM stopped working. And IKVM is one of those open source technologies that's developed by one person, Jérôme Freitas, who spent 20 years of his weekends developing it and eventually got bored with it and decided to stop. And you know, we're always exposed to the risk of developers losing interest in what they're doing. And that's what happened. So we had to find a new way of doing Saxon on .NET. And what we did was we wrote a source code transpiler from Java to C#. And I described at Markup UK last year how we wrote that transpiler and of course we wrote it in XSLT. How else would you do it? I mean, transpiling one language to another is just a question of taking the syntax tree, turning it into XML, doing an XML transformation, and then serializing the XML as a different language. It's simple, isn't it? But the consequence of doing that was that bytecode stopped working. And so this project was to say, is there something we can do instead to compensate for the fact that our .NET users have lost bytecode generation? Is there something else we can offer them in lieu? This picture is me having a bright idea and my colleague saying, "Are you sure?" So I thought I'd try out this idea of expression elaboration, which we'd used on the JavaScript project, and it had been extremely successful there. so it having been very successful with JavaScript, I thought, let's see what happens if we do that in Java and C#. So what is expression elaboration? Well, the first time we visit an expression at runtime, what we do is we take that node on the expression tree and we convert it to a Lambda expression, to a Lambda function. So we generate a function that takes the context as input and produces the value of the expression as output. And part of that is that we do the same on its, the closure of that Lambda function, the data that it has accessible to it when it executes, includes as much as possible of the data that we need as execution time as possible. So we're trying to minimize the work done each time by maximizing the amount of the work we do first time through. And part of the work we can do first time through is to elaborate the operand expressions. So instead of a tree of expressions in our expression tree, we end up with a tree of Lambda functions that invoke the function for a parent expression will have the functions for its child expressions in its closure. And then and perhaps if I show you the code, it makes a bit more sense. So here's an example, taking the negate expression again, unary minus operator. This is real code. No, I think I abbreviated it very, very slightly to take out some of the stuff that I would otherwise have had to explain. But it's essentially, it's not greatly abstracted from the actual real code. So we start up here by saying what expression are we. So this code is first time through code. We do the elaborate function once, the first time we visit a node in the expression tree to execute it. And the top half of that is evaluating some variables which end up in the closure of the function that we generate. Now there are three paths here where we generate a Lambda function. There's this path, there's this path, and there's this path. So depending on the input conditions, we generate a different Lambda function. If we know statically that the result of that $x might be an empty sequence, that affects the semantics of unary minus, and it affects it in a way that depends on whether 1-0 backwards compatibility is in force. So if it may be empty and if it's backwards compatible, then we generate a function that's going to generate double-valued.nan if it's empty. If it's not backwards compatible, then we generate null in that case, which is our representation of an empty sequence. And in the common case where it's not going to be empty, then we ignore all that runtime logic of saying, are we backwards compatible or not? And we just generate a simple call on the negate function, which is the same function that the interpreter called. And our hope is that that negate function is going to be inlined by the JIT compiler so that all that access to the closure of the method and so on all ends up. And the hope was this would achieve something very comparable to what we achieved with bytecode generation. There's one thing that we missed, and that I think accounts for some of the results that we've seen, which basically are that it's not as good as bytecode generation. And that's the fact that we are generating the same Lambda function. This bit of Java code handles all unary minus operations in the entire style sheet. It generates a different Lambda function in each case, and those differ in that they have the same code, but they have a different closure. And what seems to be happening is that the JavaScript compiler is very good at recognizing I've got two Lambda functions with the same code but different closure, and I can optimize those differently. whereas Java is saying it's the same code, so I'm going to generate the same optimization for it and not take too much account of what's in the closure. So this is a tentative conclusion, but I think we're seeing a difference in the way that different language compilers are optimizing Lambda expressions under the covers. And that's, work still to be done to determine whether that hypothesis is true. So the results that we're seeing, with JavaScript, we were getting a 5 times improvement from this kind of technique. 5 times, we didn't really measure it. You can just see it. For a 5 times improvement, you just see it go past. You say, that's okay, I'm not going to waste time measuring that. It's obviously faster. For C#, we're seeing 10% on some queries to 25% on others. So actually, it's the same order of improvement that we're getting with bytecode generation on Java. And since C# was perhaps the main focus, we can count that as a success. But what we're seeing on Java is hardly any improvement at all. And we've been doing a lot of work to try and find out why that should be. And we haven't got a complete answer to that question yet. Why do we think there are differences between platforms? Well, with JavaScript, one of the reasons was that we were starting from a much lower baseline. With Java, we've spent, 20 years almost refining the way that interpretation works and the way bytecode generation works, and they're pretty sophisticated, and an awful lot of optimizations have already gone in there. Whereas with the JavaScript platform, we were starting from something that was much simpler and didn't try to optimize anything. So that's perhaps one of the main reasons we got better success there, starting from a lower baseline. But we also think, it looks to me as if the different language processors are handling Lambda functions differently and doing different optimizations. And the significance of that is that you really need to understand the low-level machinery that you're using in order to get performance benefits at this kind of level. Measurement is so critical. Everything depends on measurement. As I say, to spot a 5 times difference, you just use the naked eye. It obviously goes faster. To spot a 10% difference, you don't need to be very elaborate in your measurement machinery. Some fairly simple measurements will show a difference of that kind of order. To spot a 1% difference, you really need to look hard, because getting Java performance results repeatable at that level of precision is really hard work. Don't try and do it on your laptop, because your laptop speed will vary by up to 5% depending on the temperature. If the room gets warmer, then the laptop is going to get slower. And that's even without the virus checker kicking in and an email arriving and processes being swapped out. It's normal to get differences of up to 10% if you do crude measurements on a laptop. So you really need to do very careful benchmarking with a machine in a controlled environment, and you need to run for hours, not for minutes. Getting that sort of accuracy of measurement really requires very, very detailed work. And the benefit is that you actually discover things you weren't expecting. So the real benefit of this project has been that by doing the measurement to find out whether this technique of elaboration worked, we actually discovered lots of other things that were much easier to fix and improve. There's this cycle that I draw there. If you measure what you've got, you understand why you're getting the measurements, and then you make improvements. And if you spend a lot of investment on measurement, you can often find there's some very easy ways of making improvements just from having the data and understanding that data. There will always be low-hanging fruit, regardless how many years you've been tweaking things. And that's certainly what we found from this exercise. So conclusions. Well, for C#, we're seeing enough benefit to suggest that it's worth putting this technique into production. Unfortunately, I was hoping that the technique might be good enough that we could get rid of bytecode generation on Java. That doesn't appear to be the case. users wouldn't thank us if we got rid of that facility and they saw a 20% slowdown on their workload as a result. We've learned an awful lot about benchmarking, and we've been able to use some of that knowledge to get performance improvements in other areas. So that's it. Thank you.
Thank you very much, Michael. We have a few minutes for question. Any question? Yeah. Yeah, look up.
So, you've put quite a lot of work into doing this. Why didn't you just take that, whatever it was, IJXML, or whatever it was called at the beginning, that's the implementer stopped working on, and just take it over and fix it?
Sorry, take what over?
That thing that converted bytecode to bytecode.
Oh, one of our customers has actually attempted to do that. And we decided to keep a watching eye on that project and see how they got on. And they were struggling with it. I didn't think it was a good idea to attempt, because although the product was IKVMC was open source, there was no test material. And I don't fancy changing a complex bit of open source software like that without any test material to check whether the changes I've made will kill it. So no, it didn't. And I had no idea of the scale of the task, because we don't understand .NET bytecode and all the things it's doing well enough. So, yeah.
Another question?
Thank you. So you handle C# and Java differently. How is this handled by the transpiler from Java to C#? Is there a lot of extra code to do the elaboration stuff in C#?
No, that part is actually very common. One of the interesting things in doing the transpiler was to discover that there are some things that are very similar between Java and C# at source level, and there are some things that are quite different. But actually, Lambda functions are very, very similar between the two languages, and therefore there's a few differences in typing, for instance, on arguments and things, but by and large, converting Java Lambda functions into C# Lambda functions was very straightforward. Yeah.
One more question?
I was wondering if you've looked at what other implementers of dynamic languages on top of the JVM have done in terms of some of these implementation things. I was specifically thinking about the improvements the JRuby people were able to get in a lot of probably not entirely unrelated areas with things like invoke dynamic and other.
I'm sorry, I'm having trouble following with the.
So other implementations of dynamic languages on the JVM.
Right.
Specifically, I remember that JRuby were able to achieve significant performance increases with certain tricks that became available.
No, I'm sorry, but the answer is no. I haven't looked at it. But thanks for the suggestion.
So we have time for one more question?
You hinted that the benchmarking and measurements that you did found a number of other opportunities for performance improvements. I just wondered what some of those were.
The way we found most of them was actually looking at allocations of objects, in particular allocations of objects that weren't immediately garbage collected in the sort of very local garbage collection that the JVM does nowadays. We found some gross bugs where we were allocating things completely unnecessarily that turned out to be on paths that were executed much more frequently than we thought they were. One of the things we've looked at more recently, we've put very little performance attention comparatively into the Saxon compile time versus the runtime. We've tended to focus on runtime performance and tended to assume that compile time is free because it's amortized. That's not true for all workloads. there are workloads where compile time is completely dominates over execution time. So profiling some of the compile time, we've found things that, you know, have been lingering there for years because we've never really looked at that hard.
Thank you very much.
Okay, thank you.